I'm Nikko Miniello.
I'm Joshua Gonzalez.
And welcome to our presentation on Gearbox reduction design. First, we're going to talk to you about the introduction, and we're going to go over design aspects, economics, cost, and finally calculations and the conclusion. Now, we had some specific design parameters we had to follow. The first one was that our transmitted power needed to be 6 horsepower. We also had an input to output ratio of 1,000 to 62.5 revolutions per minute. Additionally, we had an input versus output direction requirement that maintained that input versus output direction. We also had a light load or a light shock capacity. We had to make sure our volume was as small as possible for the total gearbox design, and we also had no cost limiting factors. Now, typical applications of this device include high torque applications such as drills, screwdrivers, rotary tools, stuff like that. We actually looked up a couple different designs, and we found this Fastenal F-style incline speed reducer. It weighs about 33 pounds with a max horsepower of 2.49 pounds. Oh, max horsepower of 2.49 with an output torque of 13,080 inch-pounds with an RPM of 1750 to 1,109. Price point was over $1,000 actually. It's kind of expensive compared to ours. We also found the Onvio dough and pancake reducer, and it has a high range of values, and it can also be made to be a 16:1 ratio, and it's also quite expensive.
Just reiterating over some of the important parameters, we had to keep a 16:1 drive ratio while trying to maintain the smallest volume possible. Also, cost was not a factor, and we had to keep in mind that there was a light shock endurance. If you look over to the left here at this image, this is an actual image of what our gears would look like. They're all changed gears. You can see the keyholes at the center, which is what fixes them to this collar and joins them all. On the left side, you'll see that the disassembled set, and on the right side, you'll actually see an assembled set. Just at the bottom here is a quick image to see some of the more important features of the gears so that you can get a better idea of the scale. On our design, we went forward with a titanium alloy because it's obviously a very strong material. If you'll notice here on our design, we had to keep a same direction of rotation, so the input and output are actually directly in line. We also had 8 total gears in our overall design, 4 of them with a 2-inch diameter, 4 with a 1-inch diameter, which is what gave us our 2:1 ratio between the gears. And again, the total reduction ending up totaling to be 16:1. For the overall maintenance of the gear set, there's not too much you have to do unless you want to disassemble them yourselves and just be really on top of it all. They were lubricated with a high-grade oil, so they're pretty much lubricated for life. As I said before, I mean, unless you notice something directly wrong with the gears, there should be no maintenance involved. This video was slowed down to give you a better image of how our actual gearbox works. This is the input gear here in front of you, and as you can see, you can barely notice the rotation at the end over here with the final gear due to the fact that this is already slowed down and the last gear has to make such a reduction in the speed.
Here we have the material properties of the titanium alloy, the grade 5 material that we used. Here's the cost analysis we did of our complete labor and material cost. We got the price of the material from Alibaba, it was $35 per pound. We got the cost of labor, $100 an hour, quoted from the CNC machining facility, because our material is very machinable. We got the weight of the material used, which we got from SolidWorks. We put in all of the parameters and the material specifications into our model. We calculated the total weight, which we then factored all these numbers together to get our total cost, which is $600. Here we have the analysis of our total product that we had, our machine, and the load we calculated for the pinion was 756.3, which is relatively high. So we chose the material, which was the titanium alloy, which is very strong. It has an ultimate bending strength of 270,000 and a bearing yield strength of 215,000. And the sigma bending we calculated is right here. The sigma contact wear we calculated is right there, which are both very high numbers. But since we were able to have the bending strength of the material being very strong, it was able to go beyond that number. These are the specifications of the gear that we used and the pinion. These are the specifications of the factory safety bending and the factory safety contact wear. As you can see for the pinion, it has a slightly lower number than the gear, even though we use the same number for the load upon it, which is the worst case scenario if it would transmit the maximum load across the whole system.
And as you can see, it's fairly safe, over 100% for all the categories. And in conclusion, we were successfully able to reduce the speed. We were able to safely transmit the horsepower. And things that we can do to improve upon our design would be, if we start over again, look at more resources, improve our literary survey. We could get a better quality material that's a little cheaper to manufacture, and maybe make it a little smaller if we have the time constraints to do so. And that's it. This is very much our presentation.